So today we're going to be looking at electrical power and energy as seen through the lens of the North Carolina Essential Standards. So we're going to start with electrical power. We've been looking at things like voltage and current and resistance, and we know that power was in that energy unit very, very long time ago, and we're actually going to bring all of these things together. So if you remember from a previous unit, our energy unit, we said that power was equal to the work done over time. It was the rate at which work was done. We also had another formula with power is equal to force times a velocity. Okay. And this is good for objects that are moving, especially if they're at a constant velocity or being raised up. But when we start talking about circuits, we need power as well. You get a power bill each month, right? And that all has to do with electricity. So, for circuits, we define power. It's still the rate at which work is done, but we're going to define it in terms of current and voltage. And so this is going to be power times our current, I, times our voltage, V. And just as a reminder, our unit for power is still watts. That doesn't change. Even if we change what we're using to calculate our power, the unit is still going to be watts. Okay. Now, this is one way to write for power, and this is what's seen in most standard textbooks. One funny thing that I heard as how to memorize this, but if you're in North Carolina, this is on our reference sheet, that it's poison IV. And so that's how you remember that P is equal to I times V. Poison IV. Well, if we insert Ohm's law into this, we know that V is also equal to IR. That's Ohm's law, which we've been using, or which we will use and have used in our circuits. We can actually plug that in for V. So we can actually take this whole thing in and plug it in for V. If we do that, we see that power can also equal I times IR. And of course, we're going to simplify this to P is equal to I squared times R. And so this is another way to write power. So right now we've got two ways to write power in circuits. But there's yet another way. Another way we've been using Ohm's law is solving for current, that I is equal to V over R. And so if we use I is equal to V over R, and we plug this in for I, another way that we can write power is P is equal to V over R times R. And once again, oops, sorry, not R. V. Yes, P is equal to IV. We plugged in V over R for I. We're going to multiply that by V. I'm going to simplify this to V squared over R. And so that gives us three different ways to calculate for power, and we'll use each of them depending on what's given in the question. And so how it looks on the North Carolina reference sheet is that you'll see P is equal to IV, which is our first equation, which is equal to I squared times R, which is equal to V squared over R. And so this is how it will look on your North Carolina reference sheet. We'll do one quick example with this. That also brings back another formula that's not on our reference sheet, but it's a good example to have. look at a 480 watt toaster that has a 30 coulomb charge flowing through the 2 minutes it's required to toast a slice of bread. Now, if you like burnt toast, you might use longer than 2 minutes, and you can adjust this question to your liking if you wish. So here we see our power. We know it's power because it's in watts. But here is a number we haven't seen in a while, and a unit we haven't seen in a while. This is 30 coulombs. 30 coulombs, that's a unit of charge, which we call Q. And then we also have time here. And in all of those formulas I just used, we didn't talk about time at all. In fact, we didn't talk about charge at all either, so Ms. Alford, what on earth are you doing here? Well, I want you to recall back to when we first started this unit. We had something called I is equal to Q over T. The definition of current is the amount of charge that flows in any given time. So in this case, we're going to look at 30 coulombs of charge over a time of 120 seconds. And yes, you do need to convert minutes to seconds here. So our current should be 0.25 amps. And after you find your current, we can then go back and look at our power. So we know we've got power of 480 and a current of 0.25 amps. And so if we go back and look at what we just did, so we're going to take this one step at a time. We've got power, so we could find the voltage of the toasted. So let's look at the voltage of this toaster. So if we do P is equal to IV, we would rearrange that so that we got V is equal to P over I. And we would look at 480 watts over 0.25 amps. So we could say the voltage that our toaster experiences is 1920 volts. That's much higher than what you would find in a standard outlet. So these numbers are made up, and is not necessarily representative of what you would get in your standard wall outlet. Your standard wall outlet, in the United States at least, is 120 volts, give or take a few. Okay, so we could find the voltage of our toaster, and let's see what else we can do. We could also find our resistor. We could use P equals I squared times R, or P equals V squared over R. And it doesn't matter which one of these you use, because these are all equivalent equations. If you're looking for your resistor, you can take your pick as to which one you find easier. I'm going to use the P is equal to I squared times R. I think that one's slightly easier for me, so that's what I'm going to use. Once again, we'll rearrange to get R is equal to P over I squared. And so we know that our power was 480 watts, and our current was 0.25 amps, but we have to square that. So we're going to take 480 over 0.25 squared. And we're going to find that the resistance in this toaster is 7,680 ohms. Okay, and so that's a quick example of electrical power. And the next thing we're going to look at is electrical energy. And so there's a big misnomer that what the energy company charges you is for power. And that's not actually what they charge you. If you look at your bill, you're going to see something that says kilowatt hour. And we talk about kilowatt hours, but we don't ever really understand what they mean. And we're going to fix that. We're going to actually understand what that means. So if we're looking at electric energy is, we're going to use the symbol E for energy. And we're going to take our power and we're going to multiply it by our time. So if we take our electrical energy and we're going to do power times time, the unit for all forms of energy is joule. That has not changed. So that's also a review from our previous unit. So with your electricity bill, you are charged with kilowatt hours and not with joules, but I want to show you how you can relate those to each other. Let's say you get charged 1 kilowatt hour. Well, what does that mean? Well, the first thing we have to talk about is, what is a kilowatt? A kilowatt is 1,000 watts. And then we can look at our time. So this is 1 hour. So our standard unit is seconds. So if I have 1 hour, and then I'm going to multiply that by 60 minutes per hour, and I'm going to multiply that by 60 seconds per minute, then I can say that an hour is 3,600 seconds. So if I want a kilowatt hour, what I'm going to interpret that to mean is that I'm going to take my 1,000 watts and I'm going to multiply it by my time. Well, if I'm doing watts, which is power, times time in seconds, that gives me the unit of joules. And I end up with 3,600,000 joules of energy. So, for example, if your standard household bill says that you use 217 kilowatt hours, which is quite a lot of energy for 1 month, but I have seen electricity bills that high, this would mean we would multiply that by 3.6 million joules of energy. To get 7.812 times 10 to the 8th joules of energy. So when we talk about a kilowatt hour, we're talking about a lot of energy. And what's really surprising is that it actually doesn't cost a whole lot. The running rate in North Carolina currently, it's about 10 cents per kilowatt hour. Okay. Now this varies in the summer and the winter. They have different rates for each of those seasons. It also depends on, for most people, which state they live in, but in North Carolina, it's roughly 10 cents per kilowatt hour. So if you were to use 217 kilowatt hours, you would multiply that by 10 cents. And your electricity bill, if you only use 217, would be 2170 cents. And we don't typically talk in cents like this. So instead, we would say that this is $21.70. Okay. So I want to take a quick backtrack to our toaster question. And we're going to assume once again that we're in North Carolina. And so we found all of this information about our toaster, but we didn't figure out how much it cost to run our toaster. So we're going to start with 480 watts, and we're going to turn that into a kilowatt. So this transforms, we're going to divide by 1,000. This would be 0.48 kilowatts. And then we need to multiply it by however many hours we use it for. But we only use it for 2 minutes. So 2 minutes is how many hours? Well, it's actually really convenient. If you take 2 minutes and divide it by 60, that will give you the number of hours. And then let's say we're here in North Carolina. In North Carolina, it costs 10 cents per kilowatt hour. So how much is this toaster going to cost us to have our 1 slice of bread in the morning? a grand total 0.16 cents. Now be careful and to not say that this is 16 pennies. This is actually 16/100ths of a penny. If you could take a penny and break it up into 100 teeny tiny pieces and take 16 of them, this would be your cost. Another way to write this would be $0.0016. Now, that's not a lot, and most people complain about their electricity bills, and that's practically free, so what's up? Well, if you only slice one, or only toast one slice of bread in the month and use no other electricity, yeah. If you're not using electricity, the cost is really cheap. But if you start adding up all of the slices of toast you do in any particular month, plus the refrigerator, plus the oven, plus the dishwasher, plus the washing machine and dryer, and your air conditioning, and your heater, and your Wi-Fi, and your television, and your computers, and your phones, and don't even forget the lights in your house. All of these little things add up to your grand total for your electricity bill. And we'll take a look at that in class as well. I'll show you my electricity bill and how to interpret it, so you'll understand that when you become adults paying for your own electricity.